Just want to thank all of you for coming. And um, so, as you can see by the picture, the transformer. I'm not going to be talking about this transformer, but a different type of transformer. Basically, the transformer forms the core of the current LLM revolution that we've been experiencing. So all of you are familiar with GPT. If we look into GPT, we look at the architecture behind GPT and most LLMs that are currently used. We'll see that what most of them have in common is that they deploy some form of neural network, and that neural network, that architecture, is known as transformer. So just a little bit about myself. I am Meir Perez. I am on the AI team, or I should say the OG AI team, since everyone here is doing AI. But, we've been around for 7 years. Initially, we worked on AI models applied to computer vision. Currently, my team works on AI models applied to layout, optimization, and generation. And we work quite a bit with transformers, custom transformers, which maybe towards the end I'll touch on. But to start off the talk, I want to just give a bit of a definition, give a bit of an overview. What is a transformer? So just to get some terminology out of the way, are you all familiar with large language models? Models that perform operation on language sequences or language series. One can think of a sentence as a sequence of words. So an LLM specifically, and transformers in general, are known as a sequence-to-sequence model. And we're all familiar with GPT. GPT stands for Generative Pre-trained Transformer. So it's generative in that it generates text. The type of sequence that GPT generates is natural language or text or code, but it's represented in the form of tokens, words. It's pre-trained on massive amounts of data using self-supervised learning, which I'll discuss later on in the talk. And the T in GPT stands for transformers. So just to sort of give a bit of the history behind the transformer, originally the transformer was developed to perform neural machine translation. So the original paper presented by Google in 2017 was where they presented the architecture, was initially applied to the problem of translating from English to French or English to German. And as you can see, a translator is a type of sequence-to-sequence model. In other words, the input sequence is one language, or a sequence of a series of words in one language, and the output is a sequence of words in a different language. And this was the original application of the transformer. An application that we're more familiar with is known as autoregression. Autoregression is the process of predicting consecutive words in a sequence. So we provide the model with an input sentence, and then we let the model predict consecutive words. This process is known as autoregression, in that it is learning or trying to choose the most likely upcoming word given an input sequence, based on the probability of choosing those particular words. So this is sort of a process that happens sort of inherently within GPT when we use it. And sort of these models are trained in a very specific way, which we'll discuss later on in the talk. But before we discuss that, I would like to give an overview of the architecture of the transformer. So what is a transformer? Transformer, at its heart, is an encoder-decoder architecture. So as I mentioned, it takes an input sequence of words. We then deploy an encoder to encode that input sequence of words into the vectors or float point arrays, where each word in the input sentence is represented by a float point array. And then that float point array, which sometimes is also called the hidden state, undergoes a series of transformations. And this is where the term transformer comes from. So in other words, you have a float point array that undergoes a series of transformations, and that is known as the encoding part. So in other words, the input sequence is encoded, and then once we've encoded the input, then we have what's known as a decoder, which takes those representations, or those float point representations of our input sequence, and then decodes them into an output sequence. And that is known as the decoder. If we take a deeper look inside the encoder and the decoder, we can see some of the functions or some of the transformations that occur. The first important block, which I'm going to be talking about in the next slide, is known as the attention block. The second very important block is known as the feed-forward block. Now, the feed-forward block, simply speaking, is essentially a set of mathematical transformations, non-linear mathematical transformations applied to these arrays. And essentially, these mathematical transformations contain a set of parameters, trainable parameters. So if you think of a polynomial with parameters, we can tweak those parameters in order to allow the model to produce a particular output, a desired output. And that process is known as training. So the trainable parameters of the transformer is found in the feed-forward part of the architecture. But if you had to really look into transformers, the place where the magic happens, I think, is in the attention layer. So what is attention? Okay, so simply speaking, attention allows for us to create connections or dependencies between input sequence, words at the input sequence, and words at the output sequence. So for example, if we want to translate a sentence, each word at the input will have an impact on the predicted word. And what attention does, it allows us to assign a strength or a weight of each word at the input to each word at the output. So in this case, for example, this is translating from French to English. So, sir has a very strong impact on the word sister, on predicting the word sister. And that's, in this diagram, is signified by the thickness of the line. And this process allows us to form these relationships or these connections between two sequences. So this process is known as attention. Okay, so in other words, we have an input sentence that we want to translate to an output. We can know exactly which word predicted in the output was affected by which word at the input. Okay. The next concept, which is implemented inside the transformer, is known as self-attention. Now, self-attention is the same process as attention, except instead of applying the attention process to an input and an output sequence, we apply that same process only to the input sequence. So what we're trying to do when we apply self-attention is we want to see which words in the input sequence has an impact on which other word at the input sequence. So for example, in this case, the animal didn't cross the street because it was too tired. We can see that the word it attends to the word animal. Right? There's a dependency between the word it and the word animal. And by training our neural network, this layer, the self-attention layer, starts learning to connect between words of a sentence, or words of a language. And this sort of paradigm actually allows the neural network to start learning different parts or different aspects of a language. So if we extend the self-attention mechanic by stacking multiple heads or multiple self-attention functions on top of one another, we can then train the neural network to learn different aspects of the language. So for example, we can train the neural network to learn pronouns, so whether what does it relate to? It relates to animal. We can also train the neural network to learn to make connections or relationships between objects and subjects of a sentence. That can be another head. Another head can learn to make connections between nouns and adjectives. And as we expose our neural network, as we expose our transformer to massive amounts of data, it starts learning to make these connections. And that is what's happening inside this multi-headed attention block inside the transformer. And this is essentially where the magic occurs. in terms of, we can ask ourselves, how is it possible to get a machine to really understand language? So it's these connections that the model makes between different words in a sentence at different levels that the model actually learns to understand the language. Okay, so just to sort of take a step back, we explained how words can be represented as a hidden state or as a vector of float point arrays. We explained how those arrays undergo different types of transformations, self-attention, and a feed-forward process. We also explained how we can connect the input sequence to the output sequence via encoder-decoder architecture and via cross-attention between the input and the output. And then the last part of the transformer architecture is the final layer, which here it's specified as linear softmax, but just think of that as the part of the neural network which generates the probabilities of selecting a particular word, of generating a particular word. So in other words, once we have these sequences of float point arrays, we then can go and use those float point arrays to generate or to predict which corresponding word in a particular language that we're trying to generate has the highest probability of following the previous input sequence, or of being translated from an input sequence. So that's sort of, in a nutshell, the transformer architecture. Very high level. Just before I continue, and I'm going to talk about how these models are trained, but there are different types of, or variants of transformers. The variant that I've spoken about up till now has been the encoder-decoder variant, where we have an encoder and a decoder. So we have an input that needs to be represented and the output that needs to be represented. This is typically used for machine translation purposes, but sometimes we don't necessarily need the full architecture. So let's say we want to classify a sentence into whether it's, do sentiment analysis, whether the sentence is positive or negative. So we don't need the full decoder. We can just take the encoder, we can propagate our words, our float point arrays through the encoder, we can then get an output, and then train our model to say whether the output is positive or negative. Another type of variant of the architecture is decoder only. This variant actually is what GPT is sort of built around. The use cases for a decoder-only architecture would be chatbots or text generation. And so that's sort of another variant of transformers, a common variant. Okay, so how is a transformer trained? I'm just going to give a bit of a background for those of you that aren't familiar with machine learning. So there are many different learning paradigms. So how do we teach, or how do we get a model to learn to do a particular task in machine learning? Right, so remember that what I mentioned earlier, these models contain parameters or values that can be tweaked in order to get the model to produce a particular output that we want. So the first paradigm is known as supervised learning. This is where we actually show the model what we want it to predict. So an example of this would be classification. We want to classify images into dogs and cats. We get a whole lot of data, we label them dogs and cats, and then we train the model to learn to differentiate between images of dogs and cats. The second paradigm is known as unsupervised learning. In that case, we have no labeled data, but rather we want to see in our data whether there are any patterns, whether we want to learn distributions of data points inside our data. So we want to see if, let's say, certain parts of our data cluster with others. So application for this typically would be clustering. The third, which I'm not going to go into detail, is semi-supervised. So that's where we have a few labeled points and we want to learn distributions of our data using a few points that have been labeled. And the third, which is the most important for our application, is known as self-supervised learning. In self-supervised learning, we don't have labeled data. Right? We don't go and label all the text data that we can get off the internet. We don't go and actively label it, but rather we use that data to train our model by assuming certain things about that data. So for example, let's say we want to train a model to predict consecutive words. Right? We can take all our data, all our text, and we know what the consecutive words are in a given text. In other words, we know what the upcoming, so we know the first 5 words of the sentence, and we know what the 6th word is. So we can train our model to predict the 6th word. So it's almost automatically labeled for us. So we don't need to go about labeling our own data. Rather, we can use the data as is and use the data as is to train our model. And this is the approach that is used to train transformers for autoregression. And this is actually also contributes to the massive power of these models, in that we have so much data. We have the entire internet. Right? We've got petabytes of data that we can use to train our models, and we can train massive models. And these models can then start to understand and learn patterns related to their data. So in the case of languages, it can start learning the rules of that particular language because it's exposed to so much data. So just to sort of give a very brief recap of sort of the process that we do. Typically what we implement is we implement an optimization algorithm that is used to tweak the parameters of our model. So we, let's say, have a sequence of words. We have a sentence. What we would do is we'd block out some of those words in the sentence. This is known as masking. So we block out some of the words, and we get the model to predict those blocked out words. We can also get the model to predict a sentence based on an input sentence. So we give it one sentence, we can give it a question, and then get the model to generate the answer. Right? So we get the model to generate the answer. We then compare it to what the actual answer is, or we get the model to generate the masked out, the left out words in a sentence, and compare it to what the actual word in that place was, and we can use the error between, or the difference between those two values, the error, to then go and tweak our model to minimize that error. And this is a type of optimization algorithm known as backpropagation. I'm not going to get into the details, but high level, this is what happens this is how we go about training these models. Okay, so how do we improve transformers? Okay, so we've now trained our transformer to do autoregression to predict consecutive words. It's incredible at predicting consecutive words. But what if we want our model to, I don't know, answer questions, or to summarize text, or to chat, or to perform sentiment analysis? So this is a process known as fine-tuning. I think a lot of you are already familiar with this, but we can take the pre-trained model, so in other words, GPT pre-trained transformer, and then we can fine-tune it on a specific task. And this is known as fine-tuning. That task can be supervised. So for example, if we want to do sentiment analysis, we can fine-tune our model to predict whether the sentence is positive or negative. And we don't need that much data because a lot of the features from the language is already encapsulated inside the model. So we need fewer data to fine-tune our model. And that's sort of one of the pros of this approach. So just to talk a little bit about how transformers are used at Wix. Most of you use on a daily basis almost GPT. We have many applications of GPT in product. But I just want to highlight a use case that my team has been working on. And that use case is applying transformers to generate layout of a page. So we can think of a web page as a series of components. So we can model our web page as a series of components. So we can train a sequence model to ingest that sequence of components and generate a better sequence of components. Right? In other words, we can take a layout which is poor and train our model to then go and improve or tweak or generate a better layout using the same components. So this is based on a paper that we presented last year at a conference, a paper called DLT, Diffusion Layout Transformer. It's trained using diffusion. I'm not going to get into diffusion now, but yeah, this is also a type of transformer. Transformers can also be used on images, so we can also think of an image as a series of patches, and we can train a transformer to perform tasks on image. So it's not just limited to language or to text. We can apply this same neural network architecture to any or to many different types of applications. So just to summarize, we discussed the architecture of the transformer. It's a sequence-to-sequence model. It's comprised of an encoder and a decoder. At the core of the transformer is the attention mechanism. We spoke about self-attention, multi-headed attention, that gives the transformer the ability to learn the rules of the language. We explained how these models can be trained, so the trainable parameters in the feed-forward part of the transformer can be tweaked to perform a specific task. We spoke about self-supervised learning, how we don't need label data to train these models, but rather we can use sequences of text and mask out certain parts of that sequence in order to get the model to predict those masked and next sentences. And finally, we ended up discussing some applications and some alternative architectures, and and how those models can be improved. Thank you.